Tonight, we're going to journey somewhere no human could ever survive. Somewhere so extreme that the laws of physics as we understand them start to blur. We're going inside a neutron star. Not near it, not orbiting it, inside it. Because here's what most people don't realize. A neutron star isn't just a dead star that collapsed. It's a place where matter itself is crushed so violently that atoms cease to exist. Protons and electrons are literally squeezed together until they merge. The density is so unimaginable that a single teaspoon of this material would weigh about 4 billion tons on Earth. And the deeper you go, the stranger it gets. Because at the very core, physicists genuinely don't know what matter becomes. We might be dealing with states of existence that don't occur anywhere else in the entire universe. Before we get started, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know, but probably haven't thought about deeply. Stars die. You've heard that before. You know that stars are born, they burn for millions or billions of years, and eventually they run out of fuel. But what you might not have considered is that the way a star dies depends almost entirely on one thing: its mass. And for a very specific range of masses, the death of a star produces something so extreme, so violent, so fundamentally strange, that it challenges the limits of what physics can describe. To understand what a neutron star is, you first have to understand what creates one. And that means understanding the life and death of a massive star. Not a star like our sun. Our sun is relatively modest. It's a middle-aged yellow dwarf, burning hydrogen in its core, converting it to helium through nuclear fusion. It's been doing this for about 4.5 billion years, and it'll keep doing it for another 5 billion or so. When the sun eventually dies, it will swell into a red giant, shed its outer layers into space, and leave behind a white dwarf. A dense, cooling remnant about the size of Earth. That's it. A quiet retirement for a quiet star. But some stars are not quiet. Some stars are monsters. Stars that are 8 or more times the mass of our sun live very different lives and die very different deaths. These are the massive stars, the blue giants and supergiants. Stars like Betelgeuse in the constellation Orion, or Rigel, the bright blue star marking Orion's foot. These stars are enormous. They can be tens of thousands of times more luminous than the sun. Some are so large that if you place them where the sun is, their surfaces would extend past the orbit of Jupiter. And here's the critical thing about massive stars. They burn through their fuel far faster than smaller stars. You might think a bigger star with more fuel would last longer, but the opposite is true. A massive star's core is under so much more gravitational pressure that fusion reactions run at a dramatically higher rate. A star like our sun will burn for roughly 10 billion years. A star 20 times the mass of the sun might last only 8 to 10 million years. That sounds like a long time by human standards, but in cosmic terms, it's the blink of an eye. The sun has been burning for 4.5 billion years. A massive star burns through its entire life in less than 1% of that time. It lives fast, and it dies hard. Now, here's what makes the death of a massive star different from the death of a smaller star. It comes down to what's happening in the core. In the sun, hydrogen is being fused into helium. When the sun eventually runs out of hydrogen in its core, it will start fusing helium into carbon and oxygen. But that's about as far as the sun can go. it doesn't have enough mass to generate the temperatures and pressures needed to fuse carbon. So it stops there and slowly dies. A massive star doesn't stop at helium. It has enough gravitational pressure in its core to keep going. After hydrogen fuses into helium, the core contracts a little, heats up, and helium begins fusing into carbon. When the helium runs out, the core contracts again, heats up further, and carbon begins fusing into neon. Then neon fuses into oxygen, then oxygen into silicon. Each stage requires higher temperatures and pressures than the last, and each stage produces less energy and lasts for a shorter time. Hydrogen burning in a massive star might last millions of years. Helium burning lasts hundreds of thousands of years. Carbon burning lasts perhaps a few hundred years. Neon burning lasts about a year. Oxygen burning might last several months. And silicon burning, the final stage, lasts roughly 1 day. 1 single day. Think about that progression. The star spent millions of years burning hydrogen, and now, in the final chapter of its life, it's burning through silicons in 24 hours. The pace of events is accelerating catastrophically, and here's why silicon burning is the end of the line. When silicon fuses, it produces iron. Specifically, iron 56, the most tightly bound nucleus in nature. This is important. Every fusion reaction before this point released energy. Fusing hydrogen into helium releases energy. Fusing helium into carbon releases energy. All the way up the chain, energy is released because the products are more tightly bound than the reactants. The nuclei are moving toward a more stable configuration, and that transition releases energy. But iron is the peak. Iron 56 has the highest binding energy per nucleon of any element. You cannot extract energy by fusing iron into heavier elements. Fusing iron doesn't release energy. It requires energy. It's an endothermic reaction. This is the fundamental dead end of stellar fusion. The star has been generating energy through fusion for its entire life, and that energy is what creates the outward pressure that supports the star against the inward pull of gravity. For millions of years, these two forces have been in balance. Gravity pulling inward, fusion pushing outward, a cosmic tug of war. But now, with an iron core accumulating at the center, the star has hit a wall. The iron core is growing as silicon fusion continues in a shell around it, dumping more and more iron onto the core, but the core itself isn't generating any energy. It's just sitting there, getting heavier. And here's where things start to go very wrong very quickly. The iron core is supported by electron degeneracy pressure. This is a quantum mechanical effect. Electrons, like all fermions, obey the Pauli exclusion principle. No two electrons can occupy the same quantum state in the same location. When matter is compressed, electrons resist being squeezed into the same states. This resistance creates a pressure that holds the core up, but electron degeneracy pressure has a limit. As the iron core grows, as more iron is dumped onto it from the silicon burning shell above, the core approaches a critical mass. This limit is called the Chandrasekhar limit, named after the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s. The limit is about 1.4 times the mass of the Sun. When the iron core reaches this mass, electron degeneracy pressure can no longer support it. What happens next is one of the most violent events in the universe. And it happens fast. Unbelievably fast. The core collapses. In less than a second, the iron core, which was roughly the size of a small planet, a few thousand kilometers across, implodes to an object about 12 miles across. the collapse happens at speeds of up to about 23% of the speed of light. That's roughly 70,000 kilometers per second. An object the size of a planet compressing to the size of a city in a fraction of a second. During this collapse, the density and temperature in the core skyrocket. The temperature reaches over 100 billion degrees. At these extreme conditions, something remarkable happens. The iron nuclei that have been accumulating are ripped apart. The intense energy breaks them back down into individual protons and neutrons. This process is called photodisintegration. Every bit of fusion the star achieved over millions of years is undone in milliseconds. The carefully constructed iron nuclei are shattered. Billions of years of nuclear evolution reversed in an instant. But that's not all. At these incredible densities, protons and electrons are forced together. The pressure is so extreme that electrons are literally squeezed into protons. When an electron combines with a proton, it produces a neutron and a neutrino. This process is called inverse beta decay, sometimes called electron capture. It happens throughout the collapsing core simultaneously. Trillions upon trillions of protons are converted into neutrons in less than a second. The neutrinos produced by this process are almost beyond comprehension in their number and energy. In that fraction of a second, the collapsing core releases more energy in neutrinos than the Sun will produce in its entire 10 billion year lifetime. About 99% of the gravitational energy released during the collapse is carried away by neutrinos. These ghostly particles, which barely interact with matter under normal circumstances, are produced in such staggering quantities that they carry away roughly 3 times 10 to the 46th joules of energy. That number is so large, it's essentially meaningless in human terms. It's more energy than you could produce by converting the entire mass of Jupiter directly into energy using Einstein's famous equation. And it all happens in about 10 seconds. Now, the core has collapsed. It's been compressed from something the size of Earth to something roughly 20 kilometers across. The matter in this core is now almost entirely neutrons, packed so tightly that the density is comparable to the density of an atomic nucleus. We've gone from normal matter, from atoms with vast spaces between their nuclei and electrons, to matter where those spaces no longer exist. The atoms have been crushed out of existence. There are no more atoms, no electrons, no protons in any meaningful sense, just neutrons, packed together so closely that the entire object is essentially one enormous nucleus. And at this point, something stops the collapse. The neutrons, like electrons, are fermions. They obey the Pauli exclusion principle. As the core compresses, neutrons resist being squeezed into identical quantum states. This creates a new form of pressure called neutron degeneracy pressure. Combined with the repulsive component of the strong nuclear force, which kicks in at extremely short distances between nucleons, this pressure halts the collapse. The core bounces. And when I say bounces, I mean that almost literally. The inner core, which has been compressed beyond its equilibrium density, rebounds outward. This rebound sends a shock wave racing outward through the still infalling outer layers of the core. For a brief moment, the infalling material from the outer core meets this outward moving shock wave, and the result is a catastrophic collision of matter, moving at significant fractions of the speed of light. But the shock wave alone isn't enough. As it moves outward, it runs into the outer core material still falling inward, and it loses energy. It stalls. If nothing else happened, the shock wave would die, and the entire star would collapse into a black hole. This was a major puzzle in astrophysics for decades. The mechanism that revives the shockwave and actually produces the supernova explosion is still an area of active research. But the leading theory involves those neutrinos. Remember the unimaginable flood of neutrinos produced during the collapse? Neutrinos barely interact with normal matter. Under ordinary circumstances, a neutrino can pass through a light year of solid lead without hitting anything. But the material just above the collapsed core is anything but ordinary. It's incredibly dense, and even though neutrinos interact only weakly with matter, there are so many of them, carrying so much energy that a small fraction of them, maybe 5%, deposit their energy into the material behind the stalled shockwave. This energy injection is enough to revive the shockwave and drive it outward through the rest of the star. The result is a supernova explosion. The outer layers of the star, everything above the collapsed core, are blasted outward at speeds of up to 30,000 kilometers per second, about 10% of the speed of light. The explosion is so bright that for a few weeks, a single supernova can outshine its entire host galaxy, billions of stars combined. This is a core collapse supernova, specifically classified as a Type II supernova, when hydrogen is present in the spectrum of the exploded material. It's one of the most energetic events in the universe. The material blasted outward by the explosion enriches the surrounding space with heavy elements: carbon, oxygen, silicon, iron, and through the extreme conditions of the explosion itself, elements heavier than iron like gold, platinum, and uranium are created and scattered into space. These elements will eventually become part of new clouds of gas and dust, which will collapse to form new stars and planets. Every atom of iron in your blood, every atom of calcium in your bones, every atom of oxygen you're breathing right now was forged in the core of a massive star and scattered into space by a supernova explosion. You exist because stars died. But the explosion is not the end of the story. It's the beginning of a different story. Because behind that expanding cloud of debris, at the center of the explosion, something remains: the collapsed core, a ball of neutrons about 20 kilometers across, containing roughly 1.2 to over 2 times the mass of our sun. An object so dense that a sugar cube-sized piece of it would outweigh every ship in the United States Navy combined. An object spinning hundreds of times per second, radiating intense beams of electromagnetic radiation from its magnetic poles. A neutron star. Now, it's important to understand the mass window here because it determines everything. Not every massive star produces a neutron star. If the original star is too small, less than about 8 times the mass of the sun, the core never gets hot enough or heavy enough to undergo this catastrophic collapse. Instead, the star ends its life as a white dwarf, supported comfortably by electron degeneracy pressure, never reaching the Chandrasekhar limit. These are the quiet deaths. The gentle fading of smaller stars into dense but relatively unremarkable remnants. On the other end, if the original star is too massive, roughly above 20 to 25 solar masses, depending on the models and the metallicity of the star, the core that remains after the explosion is too heavy. Even neutron degeneracy pressure and the repulsive nuclear force cannot hold it up. The core collapses past the neutron star stage and becomes a black hole. A region of space where gravity is won completely, where matter has been compressed to a singularity, and where nothing, not even light, can escape. The neutron star exists in between these two outcomes. It occupies a narrow window where the mass is high enough to crush atoms out of existence, but not so high that everything collapses into a black hole. It exists in a precarious equilibrium caught between two extremes, and that balance is maintained by some of the most extreme physics in the universe. Let me give you a sense of just how extreme the conditions during this collapse are, because the numbers themselves tell a story that words alone cannot. The collapse takes less than 1 second. In that time, the core goes from roughly 10,000 kilometers across to roughly 20 kilometers across. That's a compression ratio of about 500 to 1 in radius, which means more than 100 million to 1 in volume. If you compress the entire Earth by the same ratio, it would fit inside a ball about 60 meters across, roughly the length of an Olympic swimming pool. All of Earth's mass, every continent, every ocean, every mountain, compressed into something the size of a large building. That gives you a rough analogy for what happens to the core of a massive star. But the neutron star is far denser than that analogy suggests, because the core of the star was already much denser than Earth before the collapse began. The iron core, just before collapse, has a density of about 10 million kilograms per cubic centimeter. After the collapse, the density in the neutron star reaches a value comparable to the density inside an atomic nucleus itself. Under normal circumstances, atomic nuclei are tiny. They occupy an almost vanishingly small fraction of an atom's total volume. If an atom were the size of a football stadium, the nucleus would be a marble on the center of the pitch. The rest is empty space where electrons orbit. In a neutron star, all of that empty space has been eliminated. The matter has been compressed to the point where nucleons, the protons and neutrons that make up atomic nuclei, are touching each other everywhere. The entire star is essentially one continuous nuclear fluid. We will explore just how extreme this density truly is shortly, but for now understand that nothing in your everyday experience comes remotely close. To put this in perspective, consider that the densest material you will ever encounter in your everyday life is something like gold or platinum. These feel heavy in your hand. They feel substantial. Neutron star material is roughly 10 trillion times denser than gold. That ratio is so extreme it defies analogy. It's like comparing the width of a single atom to the distance from Earth to Saturn. Neutron star material is so dense that ordinary comparisons break down. There is simply nothing in everyday human experience that prepares you for this level of compression. The gravitational field at the surface of a neutron star is equally extreme. The surface gravity is about 200 billion times stronger than Earth's surface gravity. If you could somehow stand on the surface of a neutron star, which you obviously couldn't because you'd be instantly crushed into a thin layer of subatomic particles, you would weigh about 200 billion times more than you do on Earth. A person who weighs 70 kilograms on Earth would weigh roughly 14 trillion kilograms on the surface of a neutron star. Your body would be flattened into a layer less than an atom thick in a tiny fraction of a second. The escape velocity at the surface, the speed you'd need to reach to leave the neutron star's gravitational pull, is about 100,000 to 150,000 kilometers per second. That's roughly 1/3 to 1/2 the speed of light. For comparison, the escape velocity from Earth's surface is only about 11.2 kilometers per second. The neutron star's escape velocity is more than 10,000 times higher. Light itself is noticeably affected by the gravitational field. Photons climbing out of a neutron star's gravity well lose energy. their wavelengths stretched by the intense gravity. This is called gravitational redshift, and on a neutron star, it's significant. Light from the surface is redshifted by roughly 20 to 30%. This isn't a subtle effect. It's directly measurable, and it has been measured through observations of X-ray emission from neutron star surfaces. The temperature of a newly formed neutron star is extraordinary. Immediately after formation, the core temperature is around 100 billion degrees Kelvin. The surface, which cools faster because it radiates energy into space, starts at roughly 10 million degrees Kelvin or more. Over thousands of years, it gradually cools to about 1 million degrees Kelvin. Even so, a neutron star remains incredibly hot long after its formation, radiating primarily in X-rays. This is why many neutron stars are detected as X-ray sources by space telescopes. The rotation of a neutron star is another consequence of the collapse. The original massive star was rotating slowly, perhaps completing one rotation every few weeks or months. But as the core collapses, the same principle that makes a figure skater spin faster when they pull their arms in applies here. Conservation of angular momentum. When the core shrinks from thousands of kilometers across to just 20 kilometers, it speeds up dramatically. A newly formed neutron star can rotate dozens of times per second. Some neutron stars, called millisecond pulsars, rotate hundreds of times per second. The fastest known pulsar, PSRJ 1748-24468, rotates 716 times per second. The surface at the equator of this pulsar is moving at roughly 24% of the speed of light. The magnetic field also gets amplified during the collapse. Stars have magnetic fields. Our sun has a modest magnetic field, but when the core collapses, the magnetic field lines are compressed along with the matter. This amplifies the field enormously. A typical neutron star has a magnetic field of about 1 trillion Gauss. For comparison, Earth's magnetic field is about half a Gauss. A refrigerator magnet is about 50 Gauss. An MRI machine operates at around 10,000 Gauss. A neutron star's magnetic field is roughly 1,000,000 times stronger than the most powerful sustained magnets we've ever built on Earth. And some neutron stars, called magnetars, have even stronger fields, up to 1 quadrillion Gauss. These are the most powerful magnetic fields known to exist anywhere in the universe. A magnetar's field is so strong that it would be lethal from a distance of roughly 1,000 kilometers. The field would distort the electron clouds around atoms in your body, disrupting chemistry at a fundamental level. At closer range, the magnetic field would literally reshape atomic orbitals, making normal matter impossible. These magnetic fields are strong enough to bend light through a process called vacuum birefringence, which was predicted by quantum electrodynamics but is almost impossible to observe under normal conditions because you need extraordinarily strong fields. Neutron stars provide exactly those conditions. So what we're left with after the supernova clears is this: an object roughly the size of a city, containing more mass than our sun, spinning anywhere from a few times a second to hundreds of times a second, surrounded by a magnetic field trillions of times stronger than Earth's, with a surface gravity 200 billion times what you experience standing on the ground right now, with matter compressed to the density of atomic nuclei throughout, and with a surface temperature of about 1,000,000 degrees. This is a neutron star, and everything I've described so far, the formation, the collapse, the extreme conditions, all of this is relatively well understood. The physics of how neutron stars form is supported by decades of observation, by the detection of neutrinos from supernova 1987A in the Large Magellanic Cloud, by gravitational wave detections, by X-ray observations from space telescopes, and by detailed computer simulations that can model the collapse and explosion in 3 dimensions. But here's what makes neutron stars truly fascinating. Everything I've just told you is really just the beginning. Because while we understand fairly well how neutron stars form, what's inside them, what the matter actually looks like at these extreme densities, that's where things get really interesting and really uncertain. The surface and outer layers we understand reasonably well, but the deeper you go, the more uncertain our knowledge becomes, and at the very center, in the inner core, we genuinely do not know what state matter is in. The physics that governs the core of a neutron star is beyond what any laboratory on Earth can currently test. We can't recreate those densities. We can't compress matter that much. We're operating at the frontier of human knowledge, in a regime where the fundamental forces of nature, gravity, the strong nuclear force, the weak nuclear force, and electromagnetism are all operating at extreme intensities simultaneously. The neutron star is, in a very real sense, the most extreme laboratory in the universe, and what happens inside it from the crust to the core is what we're going to explore next. So now we have this object, this impossibly dense remnant sitting at the center of an expanding cloud of supernova debris, an object 20 kilometers across, containing more mass than the sun, spinning hundreds of times per second, radiating X-rays into space, a neutron star. But here's the question that should immediately come to mind. Why does it stop collapsing? Think about what just happened. Gravity crushed the iron core of a massive star so violently that it obliterated atoms themselves. It squeezed protons and electrons together until they merged into neutrons. It compressed matter from the size of Earth to the size of a small city in less than a second. Gravity did all of that. Gravity is relentless. It doesn't get tired. It doesn't take breaks. It's always pulling, always compressing, always trying to make things smaller and denser. So why doesn't gravity just keep going? Why doesn't the neutron star continue collapsing until it becomes a black hole? What force in the universe is powerful enough to stand against this level of gravitational compression and say no further? The answer lies in one of the strangest and most counterintuitive areas of physics: quantum mechanics. Specifically, a principle that governs the fundamental behavior of certain subatomic particles. To understand what holds up a neutron star, you first need to understand something about the quantum world. In quantum mechanics, particles come in 2 fundamental types: bosons and fermions. Bosons are particles like photons, the particles of light. They're sociable. They're happy to pile into the same quantum state. In fact, this is what makes lasers work. Photons are all occupying the same state, moving in lockstep. Fermions are different. Fermions include electrons, protons, and crucially for our story, neutrons. Fermions obey a rule called the Pauli exclusion principle, named after the Austrian physicist Wolfgang Pauli, who formulated it in 1925. The Pauli exclusion principle states something deceptively simple. No 2 identical fermions can occupy the same quantum state simultaneously in the same location. This might sound abstract, but its consequences are profound. It's the reason matter has structure. It's the reason atoms have electron shells. It's the reason the periodic table exists. It's the reason you don't fall through your chair right now. When electrons in an atom are forced into lower energy states, and all those states are occupied, additional electrons must go into higher energy states. They can't double up. They're forbidden from sharing. This creates the shell structure of atoms, which determines chemistry, which determines everything about the material world you experience every day. Now, apply this principle to what's happening inside a neutron star. The core has collapsed. Neutrons are being packed closer and closer together. As they're compressed, they're forced into higher and higher energy states. Because the lower energy states are already occupied, remember, they can't share. Each neutron must have its own unique quantum state. As you try to compress them further, you'd need to force them into states with even higher energy. But higher energy states mean the neutrons are moving faster, pushing back against whatever is compressing them. This resistance, this quantum mechanical pushback against compression, creates a pressure. It's called neutron degeneracy pressure, and it's what holds up a neutron star. This is fundamentally different from the kind of pressure that supports a normal star. In a main sequence star like the Sun, what prevents collapse is thermal pressure. The nuclear fusion reactions in the core produce enormous amounts of heat. That heat creates pressure that pushes outward against gravity. It's a straightforward balance. Fusion generates heat. Heat creates pressure. Pressure resists gravity. If fusion stops, the pressure drops and the star contracts. But neutron degeneracy pressure has nothing to do with heat. It would exist even if the neutron star were at absolute zero temperature. It's not generated by any energy source. It's a fundamental consequence of quantum mechanics, of the nature of fermions themselves. You could cool a neutron star to the coldest temperature imaginable, and neutron degeneracy pressure would still be there, still holding the star up. This makes a neutron star fundamentally different from a normal star. A normal star is in a delicate balance that depends on ongoing fusion reactions. Stop the fusion, and the star collapses. A neutron star doesn't need any energy source to maintain its structure. The quantum nature of neutrons themselves provides the support. It will hold its shape essentially forever, at least until something adds enough mass to push it over the edge. Let me try to make this more intuitive, because quantum degeneracy pressure is one of those concepts that's easy to describe mathematically, but hard to feel in your gut. Imagine a room full of people. Now imagine the room starts shrinking. At first, people can move around freely. There's plenty of space. But as the room gets smaller, people start bumping into each other. They resist being compressed because they take up space. Now, imagine these people have a strange rule. No two of them can stand in exactly the same spot, in exactly the same posture, at exactly the same time. As the room shrinks further, people have to adopt increasingly unusual postures to avoid duplicating each other. Some stand on one foot, some crouch, some wave their arms in unique ways. The smaller the room gets, the more energetic and agitated these postures become. People are moving faster, pushing harder against the walls, trying to maintain their unique positions. The walls of the room feel enormous pressure from all these people trying desperately not to be in the same state as anyone else. That pressure, that resistance to compression, driven by the requirement that everyone must be different, that's analogous to degeneracy pressure. It's not heat, it's not energy from some reaction. It's the fundamental refusal of fermions to be identical in the same space. Now, you might recall that I mentioned electron degeneracy pressure earlier when discussing the iron core before collapse. Electrons are also fermions. They also obey the Pauli exclusion principle, and electron degeneracy pressure is what supports white dwarf stars, the remnants of smaller stars like our Sun. So why didn't electron degeneracy pressure save the iron core? Why did it fail? The answer comes down to the Chandrasekhar limit. Subrahmanya and Chandrasekhar showed in the 1930s that there's a maximum mass that electron degeneracy pressure can support. That limit is about 1.4 solar masses. Above this mass, gravity overwhelms the electrons. It forces them to combine with protons, converting them into neutrons through inverse beta decay. The electrons essentially disappear, merged into neutrons. Their degeneracy pressure vanishes, but neutrons are also fermions. So, when the core collapses past the electron degeneracy limit and converts into a ball of neutrons, a new form of degeneracy pressure kicks in. Neutron degeneracy pressure. And neutrons, being much more massive than electrons, about 1,836 times more massive, can provide much more pressure at the same density. This is partly because of how quantum mechanics works at these scales. The uncertainty principle, another fundamental quantum mechanical relationship, connects a particle's position and momentum. When you confine a particle to a smaller space, its momentum increases. Since neutrons are much heavier than electrons, their increased momentum at a given confinement translates to much greater force. Additionally, neutrons can be packed much more densely before the Pauli exclusion principle forces them into extremely high energy states. The result is that neutron degeneracy pressure can support much more mass than electron degeneracy pressure. While electron degeneracy pressure fails at about 1.4 solar masses, neutron degeneracy pressure can support significantly more, but it too has a limit. And that limit brings us to one of the most important numbers in all of astrophysics, the Tolman-Oppenheimer-Volkoff limit. This limit is named after Richard Tolman, J. Robert Oppenheimer, yes, the same Oppenheimer who later directed the Manhattan Project, and George Volkoff. In 1939, Oppenheimer and Volkoff published a landmark paper calculating the maximum mass that a neutron star could have before even neutron degeneracy pressure fails and the star collapses into a black hole. Their original calculation, using a simplified model of neutron star matter, gave a limit of about 0.7 solar masses. But this was too low. We've since observed neutron stars with masses well above that. The problem was that Oppenheimer and Volkoff's calculation didn't account for all the physics involved. They treated neutrons as a non-interacting ideal gas. In reality, neutrons at these densities interact strongly with each other through the nuclear forces, and these interactions significantly affect the pressure. Modern calculations, which include the effects of nuclear interactions, give a Tolman-Oppenheimer-Volkoff limit somewhere between about 2.2 and 2.9 solar masses. The exact value is one of the most important unsolved problems in astrophysics because it depends on the equation of state of matter at nuclear densities. The equation of state is essentially a relationship between pressure and density. It tells you how much pressure you get for a given density. And at the extreme densities inside a neutron star, we don't know the equation of state precisely because we can't recreate these conditions in laboratories on Earth. The best constraints we have come from observations. Astronomers have measured the masses of several neutron stars with high precision using techniques like pulsar timing. In binary systems where a pulsar orbits another star, the incredibly precise timing of the pulsar's radio pulses allows astronomers to measure the orbital parameters with extraordinary accuracy, which in turn gives precise mass measurements. The most massive neutron star measured with high confidence is PSRJ 0952-0607, which has a mass of about 2.35 solar masses, though this measurement has some uncertainty. Other well-measured massive neutron stars include PSRJ 1614-2-230, with a mass of about 1.97 solar masses, and PSRJ 0348 plus 0432, with a mass of about 2.01 solar masses. These measurements are crucial because they set a lower bound on the maximum possible neutron star mass. Whatever the true Tolman-Oppenheimer-Volkoff limit is, it must be at least as high as the most massive neutron star we've observed. If our theories predicted a maximum mass lower than what we actually see, those theories would be wrong. And this constraint has already ruled out many proposed equations of state. Any equation of state that predicts neutron stars can't be heavier than about 1.5 solar masses, for example, is definitively wrong because we've seen neutron stars heavier than that. Now, I've been talking about neutron degeneracy pressure as if it's the only thing holding up a neutron star, but that's a simplification. At the extreme densities inside a neutron star, another force plays a critical role: the strong nuclear force. The strong force is one of the four fundamental forces of nature. It's the force that holds atomic nuclei together. It binds protons and neutrons into nuclei, overcoming the electromagnetic repulsion between positively charged protons. Without the strong force, every atomic nucleus heavier than hydrogen would fly apart instantly, and the only element in the universe would be hydrogen. The strong force is, as its name implies, strong. At the distances typical of nuclear structures, around 1 femtometer, which is 1 quadrillionth of a meter, the strong force is about 100 times stronger than the electromagnetic force. It's the most powerful force in nature at these scales. But the strong force has a peculiar property. It's attractive at moderate distances, pulling nucleons together, but it becomes repulsive at very short distances. Think of it like this. At a comfortable distance, nucleons attract each other, snuggling together into stable nuclei. But if you try to push them too close, closer than about 0.7 femtometers, the strong force switches from attractive to repulsive. It pushes back hard. This repulsive core of the strong nuclear force is another crucial component of what holds up a neutron star. At the extreme densities in the neutron star's interior, neutrons are packed so closely that they're well within the range where the strong force becomes repulsive. This repulsion provides additional pressure support beyond what neutron degeneracy pressure alone would give. In fact, at the highest densities found in neutron star cores, the repulsive strong force may contribute more to the total pressure than neutron degeneracy pressure does. This is one of the reasons why the original Oppenheimer-Volkoff calculation gave too low a maximum mass. They didn't include the effects of the strong force between neutrons. When you add the repulsive component of the strong force, the maximum mass goes up significantly. So the real picture is this: a neutron star is supported by a combination of two effects: neutron degeneracy pressure, which is a quantum mechanical effect arising from the Pauli exclusion principle, and the repulsive core of the strong nuclear force, which is a fundamental property of how nucleons interact at very close range. Together, these two effects create enough pressure to resist gravity and prevent the neutron star from collapsing into a black hole as long as the total mass stays below the Tolman-Oppenheimer-Volkoff limit. Let me try to give you a visceral sense of the density we're talking about, because I think the numbers I've been throwing around deserve more context. The density of neutron star material is roughly 230 million metric tons per cubic centimeter. Let me build up to that gradually so you can feel how absurd that is. Water has a density of about 1 gram per cubic centimeter. That's familiar. A cubic centimeter of water is about the size of a sugar cube. It weighs 1 gram. Iron, one of the densest common materials, has a density of about 7.87 grams per cubic centimeter. So a sugar cube-sized piece of iron weighs about 8 grams. Gold is denser, about 19.3 grams per cubic centimeter. A sugar cube of gold weighs about 19 grams. Osmium, the densest naturally occurring element on Earth, has a density of about 22.6 grams per cubic centimeter. Now let's jump to more exotic objects. The core of the Sun has a density of about 150 grams per cubic centimeter. That's about 7 times denser than gold. A sugar cube of material from the Sun's core would weigh about 150 grams, roughly the weight of a baseball. A white dwarf, the dense remnant of a small star, has a density of about 1 million grams per cubic centimeter, or 1 metric ton per cubic centimeter. A sugar cube of white dwarf material would weigh 1 ton, about the weight of a small car. That's already extraordinary. A sugar cube that weighs as much as a car. Now, a neutron star, 230 million metric tons per cubic centimeter. A sugar cube of neutron star material would weigh 230 million tons. Let me try to put that in perspective. The Great Pyramid of Giza weighs about 6 million tons. A sugar cube of neutron star material weighs roughly 38 times more than the Great Pyramid. All of the buildings in Manhattan combined weigh an estimated roughly 100 million tons. A sugar cube of neutron star material weighs more than twice that. The entire human population of Earth, all 8 billion people, weighs a total of roughly 560 million tons. You could fit the equivalent weight of roughly 40% of all humans currently alive on Earth in a single sugar cube of this material. If you placed a sugar cube of neutron star material on Earth's surface, it wouldn't sit there. It would immediately begin sinking, punching through the crust, through the mantle, all the way to the center of the planet. Nothing on Earth could support it. No structure, no material, nothing. It would fall through rock and metal like a bullet through fog. Actually, it would be far worse than that. The gravitational effects of that much mass concentrated in such a tiny volume would be devastating to the local area long before it touched the ground. This is why analogies about neutron star density always feel inadequate. We can say the numbers, we can make comparisons, but the reality is so far beyond human experience that our brains can't truly process it. We didn't evolve to understand densities like this. Nothing in our evolutionary history required us to comprehend 230 million tons packed into a cubic centimeter. Our intuition simply breaks. Here's another way to think about the density. If you took the entire mass of the Sun, 1.99 times 10 to the 30 kilograms, and compressed it to neutron star density, it would fit in a sphere about 20 kilometers across. That's roughly the distance from one side of a mid-sized city to the other. The entire Sun, all that mass, all that fire, all that plasma, compressed into something you could almost drive across in 15 minutes if there were a road. But of course, there is no road, because the surface gravity of this object would kill you. long before you got close enough to try. Now, there's something subtle and important about this balance between gravity and quantum pressure that I want to make sure you understand, because it explains why neutron stars exist in such a narrow mass range. If you start with a neutron star at, say, 1.4 solar masses, and you add mass to it, what happens depends on how much mass you add. If you add a little, the star compresses slightly. The density increases. The degeneracy pressure and nuclear force repulsion increase accordingly, finding a new equilibrium at a slightly higher density and slightly smaller radius. The star is stable. But if you keep adding mass, the compression continues. The star gets denser and denser, smaller and smaller. And there comes a point where adding more mass doesn't just compress the star a little. It pushes the pressure requirements beyond what neutron degeneracy pressure and the strong force can provide. At that point, the star collapses. There's no intermediate state. There's no softer, gentler form of support that kicks in beyond neutron degeneracy pressure. If neutron degeneracy pressure and the strong nuclear force can't hold the star up, nothing can. Gravity wins. The star collapses to a black hole. This is why the Tolman-Oppenheimer-Volkoff limit is so sharp. Below it, the neutron star is stable. Above it, collapse is inevitable. There's no gradual transition. It's a cliff edge. And neutron stars live their entire existence perched right at the edge of that cliff. Every neutron star in the universe is an object that barely avoided becoming a black hole. If the core of the progenitor star had been just a little more massive, if just a little more material had fallen back after the supernova explosion, the neutron star would have tipped over the edge and collapsed into oblivion. That's a sobering thought. Every neutron star we observe is a survivor, an object that came within a cosmic hair's breadth of becoming something from which no information can escape, something that erases all structure, all complexity, all the fascinating physics we're discussing tonight. The neutron star balanced right at the threshold, held up by the quantum stubbornness of neutrons refusing to share their states, and by the repulsive push of the strong force at extremely close range. There's also something worth mentioning about what happens to a neutron star if it does gain enough mass to exceed the Tolman-Oppenheimer-Volkoff limit. This can happen in binary systems, where a neutron star orbits another star and gradually accretes material from its companion. As matter falls onto the neutron star, its mass slowly increases. If it crosses the limit, the collapse is sudden and complete. The neutron star simply vanishes, replaced by a black hole. No explosion, no dramatic outburst, just a quiet disappearance as the event horizon forms and swallows the star. This has likely happened many times throughout the universe's history, though it's extraordinarily difficult to observe directly. But there's another way neutron stars can exceed the mass limit, and we've actually observed this one. When two neutron stars in a binary system spiral together and merge. This is what was detected on August 17th, 2017, in the event designated GW170817. Two neutron stars, each about 1.3 to 1.5 solar masses, spiraling closer and closer over billions of years as they lost energy through gravitational wave emission, finally merging in a cataclysmic collision. The gravitational waves from this merger were detected by the LIGO and Virgo observatories. The electromagnetic counterpart, a burst of gamma rays followed by a fading glow called a kilonova, was observed by telescopes around the world. This single event provided an enormous amount of information about neutron star physics. including constraints on the equation of state and the behavior of matter at nuclear densities. The total mass of the merged object was about 2.7 solar masses, well above the Tolman-Oppenheimer-Volkoff limit. The merged remnant likely survived for a brief time as a hypermassive neutron star, supported temporarily by rapid rotation before collapsing into a black hole. That brief existence, lasting perhaps milliseconds to seconds, represents a neutron star pushed beyond its limits, held up for just a moment by rotational energy before gravity claimed its final victory. This observation confirmed predictions that had been made for decades, but never directly tested. It showed that our understanding of neutron star physics, while incomplete, is on the right track. The merger produced gravitational waves that matched our theoretical predictions. The kilonova light curve matched models of heavy element production in neutron-rich material. The constraints on the equation of state were consistent with other observations. But the observation also raised new questions. The exact moment of collapse, the precise maximum mass that rotation can temporarily support, the details of what happens in those final milliseconds, all of these remain active areas of research. Let me bring this back to the big picture. A neutron star is an object held in existence by two effects: neutron degeneracy pressure, the quantum mechanical resistance of neutrons to being compressed into identical states, and the repulsive core of the strong nuclear force, the fundamental pushback that nucleons exert on each other at extremely close range. Together, these two effects create enough outward pressure to counterbalance the inward pull of gravity, but only up to a point. Beyond a certain mass, roughly 2.2 to 2.9 solar masses, not even these effects are enough. Gravity wins. The star collapses into a black hole. This balance, this precarious equilibrium between quantum physics and gravity, is what defines a neutron star. It's not just a dead star that collapsed. It's a battlefield where two of the most fundamental forces in nature are locked in a standoff. Gravity is trying to crush the star into nothing. Quantum mechanics and the strong nuclear force are pushing back, preventing that final collapse. And as long as the mass stays below the limit, this standoff holds. The neutron star persists, spinning, radiating, existing in a state of matter so extreme that it has no parallel anywhere else in the observable universe, except perhaps in the brief instance of a neutron star merger, or in the first microseconds after the Big Bang, when the entire universe was at comparable densities. But this description of the neutron star as a ball of neutrons held up by degeneracy pressure is really just the broad picture. When you look more closely, when you examine the internal structure layer by layer, the neutron star reveals itself to be far more complex and far more strange than a simple ball of compressed neutrons. It has layers. It has structure. It has regions where matter behaves in ways that exist nowhere else and may never be fully understood. The surface is one thing. The core is something else entirely. And between them is a journey through some of the most extreme and exotic physics imaginable. A journey that takes us from the relatively well understood territory of nuclear physics at the surface to the genuinely unknown frontier of fundamental physics at the center. That journey inward, from the crust to the core, is where the neutron star truly becomes remarkable. Because it turns out that a neutron star is not just a giant ball of neutrons. It's far more interesting than that. Now let's go inside. Let's take a journey from the surface of a neutron star downward, layer by layer, into the interior. And I want you to understand something important before we begin. This isn't speculation. The layered structure I'm about to describe is well supported by decades of nuclear physics research, by observations of pulsars, by gravitational wave data, and by sophisticated computational models. There are uncertainties, especially as we get deeper, but the broad picture of a neutron star's internal architecture is one of the most robust results in modern astrophysics. Think of it like understanding the interior of the Earth. We've never drilled to the center of our planet. The deepest hole ever drilled, the Kola super deep borehole in Russia, reached only about 12 kilometers down. Earth's radius is over 6,300 kilometers. We've barely scratched the surface, and yet we know with great confidence that Earth has a thin crust, a thick mantle, a liquid outer core, and a solid inner core. We know this from seismology, from studying how earthquake waves travel through the planet. Different layers transmit waves differently, and by analyzing those wave patterns, we can map the interior without ever visiting it directly. Neutron star physics works in a remarkably similar way. We've never been inside a neutron star. We never will be. But we can study how these objects behave, how they rotate, how they emit radiation, how they respond to disturbances, and from those observations, combined with our knowledge of nuclear physics, we can build a detailed picture of what's inside. So let's start at the surface and work our way down. The very outermost layer of a neutron star is its atmosphere. Now, when I say atmosphere, I don't mean anything like Earth's atmosphere. This isn't a thick blanket of nitrogen and oxygen. A neutron star's atmosphere is incredibly thin, perhaps only a few centimeters to a few meters thick. But it's important because it's what we actually see when we observe a neutron star. The atmosphere is made of whatever light elements have accumulated on the surface. Hydrogen and helium, mostly, possibly some carbon. The temperature of this atmosphere ranges from about 100,000 to several million degrees Kelvin, depending on the age and activity of the neutron star. At these temperatures, the atmosphere emits X-rays, and the spectrum of those X-rays carries information about the surface composition, temperature, and gravitational field. By analyzing X-ray spectra from neutron star atmospheres, astronomers can measure surface temperatures, infer chemical compositions, and even estimate the star's radius. The atmosphere is so thin and the gravity so strong that it's compressed into an incredibly dense layer. If you could somehow see it from the side, it would be thinner than a coat of paint on a cannonball. Beneath this whisper-thin atmosphere lies the outer crust. This is where things start to get genuinely strange. The outer crust of a neutron star extends from the surface down to a depth of roughly a few hundred meters. In this layer, matter exists in a form that's exotic by terrestrial standards, but still recognizable if you know nuclear physics. The outer crust is composed of atomic nuclei arranged in a crystalline lattice, surrounded by a sea of free electrons. Think of it like a metal, but taken to an extreme that no metal on Earth approaches. In an ordinary metal like iron, the atoms are arranged in a regular pattern, a lattice with electrons flowing freely between them. This is what makes metals conduct electricity. The outer crust of a neutron star is similar in concept, but wildly different in scale. The nuclei in this lattice are iron and other iron group elements near the surface, becoming progressively more neutron-rich as you go deeper. The pressure increases rapidly with depth, and as it does, the nuclei change. They capture electrons through inverse beta decay, the same process that happened during the core collapse. Protons in the nuclei convert to neutrons, making the nuclei increasingly neutron-rich. At the surface, you might have ordinary iron 56 nuclei. A few hundred meters down, you have exotic neutron-rich nuclei like krypton 118 or others that don't exist naturally on Earth because they'd be wildly unstable under normal conditions. But under the immense pressure of a neutron star's crust, these exotic nuclei are stabilized. The pressure holds them together. Here's what's remarkable about this crystalline lattice. It's the strongest material known to exist in the universe. The binding energy of this lattice, the energy you'd need to break it, is estimated to be about 10 billion times the strength of the strongest steel we can make on Earth. If you could somehow obtain a piece of neutron star crust and bring it back to Earth, you could not cut it, break it, melt it, or deform it with any technology available to humanity. It would be absolutely indestructible by any means we possess. This extreme strength comes from the intense electromagnetic forces between the closely packed, highly charged nuclei and the dense electron sea surrounding them. Everything is compressed so tightly that the bonds between atoms are incredibly strong. The crystal lattice is rigid, hard, and unyielding to an almost incomprehensible degree. This strength has real consequences for neutron star behavior. It means the crust can support mountains, not mountains like Everest. Mountains on a neutron star might be only a few centimeters tall at most, but given the incredible density and gravity, even a centimeter tall mountain on a neutron star represents an enormous amount of structural stress. These tiny mountains, these imperfections in the neutron star's shape, may be responsible for continuous gravitational wave emission from spinning neutron stars. A perfectly smooth, perfectly spherical neutron star spinning on its axis wouldn't emit gravitational waves, but one with even tiny asymmetries, bumps or mountains just centimeters tall, would. Gravitational wave detectors like LIGO are searching for these signals right now. As we continue downward through the outer crust, the pressure keeps rising and the nuclei keep getting more neutron-rich. They're absorbing electrons, converting protons to neutrons, becoming bloated with extra neutrons, and eventually, we reach a critical threshold. At a density of roughly 4 times 10 to the 11 grams per cubic centimeter, which is about 400 billion grams per cubic centimeter, we cross into the inner crust. And this is where something truly remarkable happens. The nuclei have become so swollen with neutrons, so overloaded with them, that they can't hold any more. Neutrons begin to leak out. They drip out of the nuclei and float freely in the spaces between them. This is called the neutron drip line, and it marks the boundary between the outer crust and the inner crust. Below this point, you have a mixture of extremely neutron-rich nuclei still arranged in a lattice, a sea of free electrons, and now a gas of free neutrons filling the space between the nuclei. The free neutrons aren't bound to any nucleus. They roam the spaces between the lattice sites, forming a fluid that permeates the crystal structure. And this neutron fluid has a property that seems almost impossible given the extreme conditions. It's a superfluid. A superfluid is a state of matter that flows with absolutely zero viscosity, no friction, no resistance to flow. If you set a superfluid in motion, it would continue flowing forever without any energy loss. On Earth, superfluidity has been observed in liquid helium cooled to temperatures near absolute zero, about 2 degrees above absolute zero, or roughly minus 271 degrees Celsius. It's one of the most exotic states of matter we can create in laboratories, and it requires extreme cold. So how can a superfluid exist inside a neutron star, where temperatures are millions or even billions of degrees? The answer is that temperature is relative. What matters for superfluidity isn't the absolute temperature, but the temperature relative to the critical temperature for the phase transition. For liquid helium on Earth, the critical temperature is about 2.2 Kelvin. That's extremely cold. But for neutrons at nuclear densities, the critical temperature for superfluidity is predicted to be around 500 million to 1 billion Kelvin. The interior of a neutron star, while incredibly hot by human standards, is actually below this critical temperature. So the neutrons form Cooper pairs, bound pairs of neutrons that together behave as bosons rather than fermions. And bosons, remember, don't obey the Pauli exclusion principle. They can all pile into the same quantum state. When they do, you get a superfluid. This neutron superfluid in the inner crust has profound consequences for how neutron stars behave. One of the most dramatic is the phenomenon of pulsar glitches. Pulsars are rotating neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like lighthouse beams. If Earth happens to be in the path of one of these beams, we see regular pulses of radio waves or X-rays. The timing of these pulses is extraordinarily precise. Some pulsars rival atomic clocks in their regularity, but occasionally a pulsar will suddenly speed up. Its rotation rate will jump by a tiny but measurable amount over a very short time, sometimes less than a minute. This is called a glitch. After the glitch, the pulsar gradually slows back down toward its original rate over a period of days to months. These glitches have been observed in hundreds of pulsars. The Vela pulsar, one of the most studied pulsars in the sky, glitches roughly every 3 years. Each glitch increases its rotation rate by about 1 part in a million. That doesn't sound like much, but for an object rotating about 11 times per second with a moment of inertia vastly greater than anything on Earth, it represents an enormous transfer of angular momentum. The leading explanation for glitches involves the superfluid in the inner crust. Here's how it works. The neutron star's solid crust is slowing down over time due to magnetic braking. The star's powerful magnetic field interacts with the surrounding environment, gradually extracting rotational energy. The crust, being solid and rigid, slows down as a unit. But the superfluid neutrons in the inner crust don't slow down at the same rate. Because they flow without friction, they're decoupled from the crust. They keep spinning at their original rate while the crust slows. Over time, a difference in rotation speed builds up between the crust and the superfluid. But the superfluid doesn't rotate smoothly like a normal fluid. Instead, its rotation is quantized. It rotates through an array of tiny quantum vortices, microscopic tornado-like structures, each carrying a fixed quantum of angular momentum. These vortices normally pin to the crystal lattice of the crust, anchored to the nuclei in the lattice. As the crust slows, the vortices remain pinned, and the superfluid maintains its faster rotation rate. But eventually, the difference in rotation between the superfluid and the crust creates too much stress. The vortices suddenly unpin, releasing their stored angular momentum into the crust. The crust speeds up. This is the glitch. Millions or billions of vortices unpinning simultaneously, dumping angular momentum from the superfluid into the solid crust, causing a sudden measurable increase in the star's rotation rate. After the glitch, the vortices gradually repin to the lattice, and the slow process of building up rotational stress begins again. This cycle repeats, producing glitches at semi-regular intervals. The study of glitches is one of the most powerful tools we have for probing the interior of neutron stars. The size and frequency of glitches tell us about the amount of superfluid in the crust, the strength of the pinning forces, and the coupling between the superfluid and the solid components. This is neutron star seismology, using the star's own behavior to map its interior, just as geologists use earthquake waves to map Earth's interior. Now, as we continue deeper into the inner crust, approaching the boundary with the core, something even stranger is predicted to happen. The neutron-rich nuclei in the lattice become larger and more deformed as the density increases. They stretch, merge, and reform into exotic geometric shapes. Physicists have given these shapes whimsical names: nuclear pasta. Just as Italian pasta comes in various shapes, spaghetti, lasagna, and so on, the nuclei in the deepest parts of the inner crust are predicted to form elongated tubes called spaghetti, flat sheets called lasagna, cylindrical holes in a neutron medium called bucatini, and spherical holes called Swiss cheese. The names are playful, but the physics is serious. These pasta phases arise because of the competition between the strong nuclear force, which pulls nucleons together, and the electromagnetic force, which pushes protons apart. At the densities found near the base of the inner crust, roughly 100 trillion grams per cubic centimeter, these forces are nearly balanced. The resulting structures depend on the exact ratio of protons to neutrons and the local density. Small changes in density produce different shapes. Computer simulations of nuclear pasta show that these phases are incredibly complex. The structures interweave and connect in three-dimensional patterns that resemble biological membranes or the large-scale structure of the universe, filaments and sheets and voids at nuclear scales. Some calculations suggest that nuclear pasta might be the strongest material in the universe, even stronger than the crystalline outer crust. The shear modulus of nuclear pasta, a measure of how resistant it is to deformation, might be 100 times larger than the shear modulus of the outer crust. If this is correct, the pasta layer plays a crucial role in the neutron star's mechanical properties. Might affect the maximum height of mountains on the neutron star, which in turn affects gravitational wave emission. It might influence how the crust cracks during starquakes, which are sudden fractures in the crust that can produce gamma-ray flares, especially in magnetars. Nuclear pasta has never been directly observed. We cannot create these conditions in any laboratory on Earth, but the theoretical predictions are robust. They come from multiple independent research groups using different computational methods, and they all find similar results. Nuclear pasta is expected to occupy a relatively thin layer, perhaps a few hundred meters thick, at the base of the inner crust. But despite being thin, it contains a significant fraction of the crust's total mass because of the extreme density. Below the pasta layer, we cross into the outer core. This is the largest region of the neutron star by volume. It extends from the base of the crust, at about half the star's radius, down to the inner core. The outer core is where most of the neutron star's mass resides. In the outer core, individual nuclei no longer exist. The density is too high. Matter exists as a continuous fluid of neutrons with a small admixture of protons and electrons, roughly 5 to 10% protons, and a corresponding fraction of electrons to maintain charge neutrality. This fluid is not a crystal. It's not a lattice. It's a liquid. Though calling it a liquid doesn't really capture how different it is from any liquid you've ever encountered. This is a quantum liquid at nuclear density. The neutrons in the outer core are also predicted to form a superfluid, similar to the free neutrons in the inner crust, but now making up the bulk of the matter rather than filling spaces in a lattice. But the protons in the outer core do something equally extraordinary. They form a superconductor. A superconductor is a material that conducts electricity with zero resistance. On Earth, superconductivity occurs in certain metals and ceramics cooled to extremely low temperatures. In the outer core of a neutron star, the protons are predicted to form Cooper pairs just like the neutrons. But because protons carry electric charge, their Cooper pairs create a superconducting state rather than a superfluid state. A neutron star's outer core is therefore predicted to be simultaneously a superfluid and a superconductor. Two of the most exotic states of matter known to physics existing together in the same region at densities and temperatures that make terrestrial superconductors and superfluids seem trivial by comparison. The superconducting protons have profound implications for the neutron star's magnetic field. In a normal conductor, magnetic fields penetrate the material uniformly. But in a superconductor, magnetic fields are confined to narrow tubes called flux tubes, or fluxoids. Each flux tube carries a quantized amount of magnetic flux. In the outer core of a neutron star, the enormous magnetic field is threaded through the superconducting proton fluid in the form of an immense number of these quantized flux tubes. The magnetic field of a neutron star is already extraordinary. A typical neutron star has a surface magnetic field of about 1 trillion Gauss, roughly a trillion times stronger than Earth's magnetic field. But this field isn't uniformly distributed through the interior. In the superconducting outer core, it's organized into flux tubes. And these flux tubes interact with the superfluid neutron vortices in complex ways. The interaction between superfluid vortices and superconducting flux tubes is one of the most active areas of neutron star research. These interactions affect how the star slows down over time, how it responds to glitches, how its magnetic field evolves over thousands and millions of years, and potentially how it emits gravitational waves. When a neutron star is born in a supernova, it's rotating rapidly and has a strong magnetic field. Over time, the magnetic field acts as a brake, gradually slowing the rotation. But the details of this braking depend on how the magnetic field is coupled to the interior. If the outer core is superconducting, the flux tubes can become entangled with the neutron vortices. As the star tries to slow down, the vortices need to move outward to reduce the star's angular momentum. But if they're entangled with flux tubes, the flux tubes are dragged along. This couples the magnetic field evolution to the rotational evolution in complex ways that we're still working to understand. Magnetars, the neutron stars with the most extreme magnetic fields, reaching up to 1 quadrillion Gauss or more, present special challenges for this picture. Their fields are so strong that they may exceed the critical field strength for proton superconductivity, potentially destroying the superconducting state in parts of the outer core. If the superconductivity is destroyed, the magnetic field would no longer be confined to flux tubes. It would permeate the core more freely, potentially rearranging itself in sudden violent events. These magnetic rearrangements might be responsible for the giant flares observed from magnetars. On December 27th, 2004, a magnetar designated SGR 1806-20 emitted a giant flare so powerful that had briefly affected Earth's ionosphere from roughly 42,000 light-years away. The energy released in a fraction of a second was equivalent to what the Sun produces in about 250,000 years. This event is believed to have been caused by a sudden, large-scale restructuring of the magnetar's magnetic field, possibly triggered by a starquake in the crust that released magnetic stresses built up over years or decades. The neutron star's rotation also connects to its observational properties in ways that depend on the internal structure. Pulsars, rotating neutron stars with misaligned magnetic and rotational axes, produce beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space. The precision of pulsar timing, the regularity of the pulses, depends on the rigidity of the crust and the coupling between the crust and the interior. Any irregularity in the interior, any interaction between the superfluid and the crust, any movement of the flux tubes can show up as tiny deviations in the pulse timing. Pulsar timing is now so precise that we can detect variations at the level of microseconds over years of observation. These tiny variations carry information about the interior. By studying how pulsars slow down, how they glitch, and how they recover from glitches, astronomers can infer properties of the superfluid, the superconductor, the crust strength, and the coupling between different layers. There's another phenomenon related to the outer core that deserves mention. Neutron stars in binary systems, those orbiting another star, can accrete matter from their companion. As matter falls onto the neutron star, it impacts the surface at speeds approaching half the speed of light. The kinetic energy of this infalling material is converted to heat and radiation, producing brilliant X-ray emission. This is why many neutron stars are observed as X-ray binaries, among the brightest X-ray sources in the sky. But the accreted material also compresses the existing crust. As more material piles on, the crust is pushed to higher densities. The nuclei in the crust undergo nuclear reactions, transforming into different isotopes as they're compressed deeper. These reactions release heat, warming the crust. When the accretion stops, the crust cools. By observing how quickly the crust cools after accretion ceases, astronomers can measure the thermal properties of the crust, including its conductivity and heat capacity. These cooling observations have confirmed many predictions about the crust's composition and structure. They've shown that the inner crust contains a superfluid component because the observed cooling rates require the enhanced heat capacity that a superfluid provides. They've also provided evidence for nuclear pasta because the thermal conductivity of pasta phases differs from that of a regular lattice, and the observed cooling curves seem to favor models that include pasta. These are remarkable achievements. We're determining the properties of matter at densities we can never recreate on Earth, using observations of objects thousands of light years away. The neutron star's own behavior is our laboratory. Its glitches, its cooling, its magnetic field evolution, its pulse timing, all of these are windows into the interior. I want to pause here and emphasize something. Everything I've described about the outer crust, inner crust, neutron drip, superfluidity, superconductivity, nuclear pasta, glitches, and magnetic field structure is well-supported science. These aren't wild guesses. They're predictions based on nuclear physics that has been tested in terrestrial laboratories, extrapolated to higher densities using well-established theoretical frameworks, and confirmed or constrained by observations. There are uncertainties, of course. The exact density at which nuclear pasta forms, the precise critical temperature for superfluidity, the detailed coupling between vortices and flux tubes, these things are still being refined. But the broad picture is solid. A neutron star has a thin atmosphere, a rigid crystalline outer crust, an inner crust with dripped neutrons forming a superfluid permeating a lattice of exotic nuclei, a transition zone of nuclear pasta, and an outer core of superfluid neutrons and superconducting protons. This structure is not controversial among astrophysicists. It's the standard model of neutron star interiors, supported by multiple independent lines of evidence. But there's one more region we haven't discussed: the inner core, the innermost part of the neutron star, where densities climb to 2, 3, 5, or even 10 times nuclear density. And it's here, in this innermost region, that our confidence begins to falter. Here, at the very heart of the neutron star, the physics we've relied on starts to become uncertain. The well-tested nuclear physics that served us so well in the crust and outer core may no longer apply. New particles may appear, new phases of matter may emerge. The fundamental building blocks of matter, quarks and gluons, may break free from their usual confinement inside protons and neutrons. And the truth is, we don't know for certain what happens there. We have hypotheses, we have models, we have constraints from observations, but we don't have answers. Not yet. The inner core of a neutron star is one of the last great frontiers in physics. A place where the extreme conditions push our understanding to its absolute limits. And exploring what might exist in that innermost region is where our journey takes us next. We've traveled from the surface of a neutron star through its crystalline crust, past the neutron drip line, through the exotic pasta phases, and into the outer core where neutrons flow as a superfluid and protons conduct electricity without resistance. Everything we've discussed so far rests on solid scientific ground. Well-tested nuclear physics, confirmed observations, robust theoretical frameworks. But now we're going deeper, into the inner core. And here, the ground beneath our feet, metaphorically speaking, becomes much less certain. The inner core of a neutron star is the region at the very center where densities climb to 2, 3, 5, or possibly even 10 times the density of a normal atomic nucleus. To put that in perspective, nuclear density is already about 230 million metric tons per cubic centimeter. At the center of a massive neutron star, we may be talking about 1 to 2 billion metric tons per cubic centimeter. These are densities that exist nowhere else, in the observable universe today. They haven't existed anywhere since the first microseconds after the Big Bang, when the entire universe was a hot, dense soup of quarks and gluons before they condensed into protons and neutrons. The only way we can probe remotely similar conditions is through particle accelerators. The Large Hadron Collider at CERN and the relativistic Heavy Ion Collider at Brookhaven National Laboratory can briefly create tiny volumes of extremely hot, dense matter by smashing heavy nuclei together at nearly the speed of light. These experiments have produced quark-gluon plasma, a state of matter where quarks and gluons are briefly freed from their confinement inside protons and neutrons. But these experiments create hot, dense matter. The interior of a neutron star is cold, dense matter. Cold in the sense that the temperature, while millions of degrees, is low compared to the Fermi energy of the particles. The physics of cold, dense matter at several times nuclear. Density is fundamentally different from the physics of hot, dense matter, and it's much harder to study experimentally. We essentially have no direct experimental data on what matter does at these conditions. We have theories, we have models, we have mathematical frameworks that we can extrapolate from lower densities. But extrapolation is dangerous in physics. The history of science is filled with examples where extrapolating a theory beyond its tested range led to spectacularly wrong predictions. And the inner core of a neutron star is very far beyond the tested range of nuclear physics. So what follows is our best understanding, our most educated guesses, constrained by observation, but not confirmed in the way that the crust and outer core physics are confirmed. Keep that distinction in mind. We're entering the frontier. The first possibility for what might happen in the inner core involves particles called hyperons. To understand hyperons, you need to know a little about quarks. Protons and neutrons are not fundamental particles. They're composite objects, each made of 3 quarks bound together by the strong nuclear force. A proton consists of 2 up quarks and 1 down quark. A neutron consists of 1 up quark and 2 down quarks. Up and down are 2 of the 6 types, or flavors, of quarks that exist in nature. The other 4 flavors are called strange, charm, bottom, and top. Under normal conditions, matter is made entirely of up and down quarks. The other flavors are heavier and unstable. A strange quark, for instance, will quickly decay into an up quark through the weak nuclear force. Strange quarks don't persist in ordinary matter, but inside a neutron star's inner core, the situation is different. The density is so extreme and the Fermi energy of the neutrons is so high that it becomes energetically favorable to create new types of particles rather than continue packing neutrons into ever higher energy states. Remember the Pauli exclusion principle. As you compress neutrons, they're forced into higher and higher energy states because no two can share the same state. At some point, the energy required to add another neutron to the top of the Fermi sea becomes so high that it's actually cheaper, energetically speaking, to create a completely different particle instead. Hyperons are baryons, particles made of 3 quarks that contain at least 1 strange quark. The lambda hyperon, for example, consists of 1 up quark, 1 down quark, and 1 strange quark. The sigma hyperons and the xi hyperons contain 1 and 2 strange quarks respectively. Under normal conditions, these particles are unstable. They decay in tiny fractions of a second, but inside the extreme environment of a neutron star's inner core, they can be stabilized. The immense density and Fermi energy make it energetically favorable for some neutrons to convert into hyperons. The appearance of hyperons would have significant consequences for the neutron star. Hyperons provide additional particle species that can share the available energy states. This relieves some of the degeneracy pressure because the total energy of the system can be lower when distributed across more types of particles. In physics terms, the equation of state becomes softer. The pressure at a given density is lower than it would be for pure neutron matter. And here's where the problem arises. A softer equation of state means less pressure support against gravity. Less pressure support means the maximum mass a neutron star can achieve is lower. When physicists calculate neutron star properties using equations of state that include hyperons, the predicted maximum mass typically comes out to around 1.4 to 1.6 solar masses. But we've observed neutron stars with masses of about 2 solar masses. Some measurements suggest even higher. This is called the hyperon puzzle, and it's one of the most significant unsolved problems in neutron star physics. The puzzle is straightforward. Theory says hyperons should appear in the inner core because the conditions favor their creation. But if hyperons appear, they soften the equation of state so much that the maximum neutron star mass drops below what we've actually observed. The observations are telling us that either hyperons don't appear, which contradicts our understanding of nuclear physics, or they do appear but something else stiffens the equation of state enough to compensate, or our understanding of how hyperons interact at these densities is incomplete. Most physicists favor the third option. At the extreme densities of the inner core, the interactions between hyperons and other baryons might be different from what we currently calculate. There might be additional repulsive forces at high densities that we haven't properly accounted for. Three body forces, interactions that involve three particles simultaneously rather than just two, might become important. These three body forces are extremely difficult to calculate, but they could provide additional stiffness to the equation of state, allowing hyperons to be present while still supporting massive neutron stars. This is an area of intense active research. Nuclear physicists are working on better calculations of hyperon interactions. Experiments at facilities like the Japan Proton Accelerator Research Complex are studying hypernuclei, atomic nuclei that contain one or more hyperons, and to better constrain these interactions. Every piece of data helps narrow down the possibilities, but the hyperon puzzle remains open. Now, let's consider an even more exotic possibility. What if the density at the center of a neutron star is so extreme that neutrons themselves cease to exist as distinct particles? Remember, neutrons are made of quarks, three quarks bound together by gluons, the carrier particles of the strong force. Under normal conditions, quarks are permanently confined inside hadrons like protons and neutrons. You can never isolate a single quark. If you try to pull a quark out of a proton, the energy you invest creates new quark-antiquark pairs, and you end up with new hadrons rather than free quarks. This phenomenon is called confinement, and it's one of the defining features of the strong force. But there's a theoretical prediction that at sufficiently high densities or temperatures, confinement breaks down. The quarks become deconfined. They're no longer bound inside individual neutrons. Instead, they roam freely in a sea of quarks and gluons. This state of matter is called quark matter, or, when it's hot, quark-gluon plasma. In the context of neutron star cores, where the temperature is relatively low, but the density is extremely high, the predicted state is called cold quark matter. If quark deconfinement occurs in the inner core, the center of the neutron star would contain a fundamentally different phase of matter from the outer regions. You'd have ordinary hadronic matter, neutrons, and protons in the outer core, transitioning to deconfined quark matter in the inner core. The nature of this transition is itself uncertain. It might be a sharp first-order phase transition, with a distinct boundary between hadronic matter and quark matter, similar to the boundary between ice and liquid water. Or it might be a smooth crossover, with matter gradually changing character as the density increases, with no sharp boundary. If the transition is first order, there could be a region at the boundary where both phases coexist, forming a mixed phase with complex geometric structures. Some models predict that this mixed phase would have its own version of pasta, with droplets, rods, and sheets of quark matter embedded in hadronic matter, or vice versa. The idea of quark cores in neutron stars is taken seriously by many physicists. There are theoretical arguments suggesting that, at several times nuclear density, The energy balance should favor deconfined quarks over confined neutrons. And some models of neutron stars with quark matter cores can successfully reproduce the observed properties of neutron stars, including their masses and radii. But there's a complication. If the quarks at the center of a neutron star are deconfined, but the temperature is low, the quarks might form their own version of Cooper pairs, analogous to what happens in superconductors. This paired quark matter is called color superconducting quark matter. Color here refers not to visible color but to the color charge of quarks, the strong force equivalent of electric charge. In color superconducting quark matter, quarks pair up in ways that depend on which flavors and colors are involved. The most symmetric form, where all three light quark flavors participate equally in the pairing, is called color flavor locked matter. This state has remarkable properties. It's a superfluid and a superconductor simultaneously. It breaks the usual symmetries of the strong force in specific ways, and it might be the true ground state of matter at the highest densities, meaning that if quark matter exists in neutron star cores, it might be in this color flavor locked phase. But proving any of this is enormously difficult. We can't create cold dense quark matter in laboratories. The heavy ion collision experiments at CERN and Brookhaven create hot quark gluon plasma, which is a different beast. To truly test whether neutron star cores contain quark matter, we need observations that can distinguish between different equations of state. And that brings us to the crucial question: how do we figure out what's actually in there? Beyond hyperons and deconfined quarks, there are other hypotheses for what might exist in the inner core. Kaon condensates and pion condensates are two possibilities. Kaons and pions are mesons, particles made of one quark and one antiquark. Under normal conditions, they're unstable, but at the extreme densities of the inner core, the conditions might favor the formation of a condensate, a state where large numbers of these particles occupy the lowest energy state simultaneously. A Kaon condensate would behave somewhat like the Bose-Einstein condensates that physicists create in laboratories on Earth by cooling atoms to near absolute zero. But instead of occurring at extremely low temperatures, this condensation would occur at extremely high densities, driven by the strong interactions between particles in the dense medium. Like hyperons, kaon and pion condensates tend to soften the equation of state. They provide additional degrees of freedom that allow the system to lower its total energy, which reduces the pressure at a given density. And like hyperons, this softening creates tension with the observed masses of heavy neutron stars. The same puzzle appears across multiple exotic matter scenarios. Theory predicts that exotic particles, or phasors, should appear at high density, but their appearance tends to reduce the maximum neutron star mass below observed values. Resolving this tension is one of the central challenges in the field. Now, let me tell you about how observations are beginning to constrain these possibilities, because this is where the story becomes truly exciting. For decades, discussions about the inner core of neutron stars were almost purely theoretical. We had models and hypotheses, but very little observational data to distinguish between them. That changed dramatically in 2017. On August 17th of that year, the LIGO and Virgo gravitational wave observatories detected a signal designated GW170817. This was not the first gravitational wave detection. LIGO had already detected gravitational waves from merging black holes, but GW170817 was different. It was the first detection of gravitational waves from the merger of two neutron stars. The signal was extraordinary. As the two neutron stars spiraled toward each other in their final moments, they emitted gravitational waves that LIGO and Virgo could track for about 100 seconds. During this time, the frequency of the gravitational waves increased from about 24 Hz to several thousand Hz as the orbit tightened and the stars spiraled faster and faster. In the final fraction of a second before merger, the gravitational wave frequency was increasing so rapidly that the signal swept through LIGO's sensitive frequency band. And here's what makes this observation so powerful for understanding the inner core. As the two neutron stars approached each other, the intense gravitational field of each star distorted the shape of the other. They raised tidal bulges on each other, similar to how the moon raises tides on Earth, but incomparably more extreme. The degree of this tidal distortion depends on how easily the neutron star material can be deformed. And how easily it can be deformed depends on the equation of state. A soft equation of state, where the pressure is relatively low at a given density, produces neutron stars that are more compact and more difficult to deform. A stiff equation of state, where the pressure is higher, produces neutron stars that are larger and easier to deform. The tidal deformability leaves a measurable imprint on the gravitational wave signal. By analyzing the gravitational waves from G by 170817, physicists extracted the first direct measurement of neutron star tidal deformability. And this measurement, combined with the observed masses of the two neutron stars, placed significant constraints on the equation of state. The results ruled out the very stiffest equations of state, the ones that predict the largest, most easily deformed neutron stars. They also disfavored the very softest equations of state. The data pointed toward a moderately stiff equation of state, one that produces neutron stars with radii of roughly 11 to 13 kilometers. This might not sound like a dramatic result, but it was groundbreaking. For the first time, we had a direct observational constraint on the properties of matter at several times nuclear density. We could rule out certain models of the inner core and favor others. Equations of state that predicted very large radii were ruled out. Equations of state that predicted extremely compact neutron stars were also disfavored. The truth, according to the gravitational waves, lay somewhere in between. The electromagnetic observations of GW170817 provided additional information. About 1.7 seconds after the gravitational wave signal, the Fermi Gamma Ray Space Telescope detected a short gamma ray burst from the same location. This confirmed the long-held theory that short gamma ray bursts are produced by neutron star mergers. In the hours, days, and weeks that followed, telescopes around the world observed a fading glow from the merger site. This glow, called a kilonova, was powered by the radioactive decay of heavy elements produced in the merger. The spectrum of the kilonova showed signatures of elements like strontium, confirming that neutron star mergers are a major production site for heavy elements. The properties of the kilonova also provided information about the fate of the merged object. The observations were consistent with the merged remnant briefly surviving as a hypermassive neutron star before collapsing into a black hole. The exact survival time of this remnant, whether it was milliseconds or seconds, depends on the equation of state and the maximum mass that rapid rotation can temporarily support. Different equations of state predict different survival times, and the kilonova observations can help discriminate between them. Since GW 170817, the field has continued to advance. The NICER instrument on the International Space Station has been measuring the radii of neutron stars by analyzing the X-ray emission from hotspots on their surfaces. As the neutron star rotates, the hotspots come in and out of view, and the light curve, the variation of X-ray brightness with time, depends on the star's size and the curvature of space around it. By modeling these light curves, NICER has measured the radii of several neutron stars. The results are consistent with the gravitational wave constraints, pointing toward radii of about 11 to 13 kilometers for neutron stars of typical mass. These radius measurements are directly related to the equation of state and therefore to what's happening in the inner core. A neutron star's radius depends on how the pressure varies with density throughout its interior. The inner core, where the density is highest, has a particularly strong influence on the overall radius. So, measuring the radius with precision effectively tells us something about the conditions at the very center of the star. Combining all these observations, gravitational waves from mergers, NICER radius, measurements, precise mass measurements from pulsar timing, and theoretical constraints from nuclear physics, the scientific community is slowly narrowing down the range of possible equations of state. We haven't identified the correct one yet, but we've eliminated many incorrect ones. The picture that's emerging is of an equation of state that's moderately stiff. Stiff enough to support neutron stars of about 2 solar masses. Soft enough to produce relatively compact stars with radii around 12 kilometers. And complex enough to accommodate some form of exotic matter in the core, though we can't yet determine what that exotic matter is. There's one more crucial point I want to make before we wrap up this journey. And it's perhaps the most important thing to understand about neutron stars. A neutron star is not just a giant neutron. This is a common misconception. People hear the name, neutron star, and they imagine a ball of neutrons. Just neutrons, all the way through, uniforms, and featureless. A big, dense, boring blob. That picture is completely wrong. As we've seen tonight, a neutron star is a richly structured object with distinct layers, each with its own unique physics. The outer crust is a rigid crystal of neutron-rich nuclei. The inner crust contains a superfluid of drip neutrons permeating an exotic lattice. The transition zone may contain nuclear pasta, one of the strongest materials in the universe. The outer core is a quantum liquid of superfluid neutrons and superconducting protons. And the inner core may contain hyperons, deconfined quarks, color superconducting matter, kaon condensates, or something else entirely. Even the term neutron star is somewhat misleading. While neutrons are the dominant component, the star also contains protons, electrons, muons, and potentially hyperons, quarks, and other exotic particles. It's not a pure neutron object. It's a complex multi-component system where several species of particles coexist and interact in ways we're still working to understand. The composition changes with depth. The physics changes with depth. The properties of matter, its viscosity, its thermal conductivity, its compressibility, its magnetic behavior, all of these change as you move from the surface to the center. A neutron star is not uniform. It's layered, structured, and extraordinarily complex. And this complexity is what makes neutron stars so scientifically valuable. They sit at the intersection of 3 of the most important branches of fundamental physics: Quantum mechanics governs the degeneracy pressure and the superfluid and superconducting states. General relativity is required to accurately describe the gravitational field and the structure of space-time around and inside the star. Nuclear and particle physics determines what particles exist and how they interact at these extreme densities. Very few objects in the universe require all three of these frameworks simultaneously. Black holes involve general relativity but not nuclear physics in a detailed way, because all the matter is hidden behind the event horizon. Atomic nuclei involve quantum mechanics and nuclear physics, but not general relativity because they're too small and too light for gravity to matter. Neutron stars are unique in requiring all three. They're the only objects where quantum mechanics, general relativity, and nuclear physics all operate at extreme intensities simultaneously. This makes them natural laboratories for testing our fundamental understanding of matter and the forces that govern it. When we measure the mass of a neutron star, we're testing general relativity. When we observe a pulsar glitch, we're probing quantum superfluidity at nuclear density. When we measure the radius from X-ray observations, we're constraining the equation of state of dense matter. When we detect gravitational waves from a merger, we're testing both general relativity and nuclear physics simultaneously. No other object gives us access to all of these regimes at once. That's why neutron stars matter so much to physics. They're not just interesting astronomical curiosities. They're fundamental testing grounds for our deepest theories about nature. Let me leave you with one final thought. We've traveled tonight from the outer atmosphere of a neutron star to its unknowable heart. We've crossed through crystalline lattices stronger than any material on Earth, through neutron superfluids that flow without friction, through tangled forests of quantum vortices and magnetic flux tubes, past sheets and rods of nuclear pasta, through a quantum ocean of neutrons, protons, and electrons behaving as superfluids and superconductors. And finally, we've arrived at the center where the density is so extreme that matter itself may transform into something fundamentally different. Something that doesn't exist anywhere else in the universe today. And the astonishing thing is this. All of this, every layer, every exotic state of matter, every extreme physical process exists within an object roughly 20 kilometers across. Smaller than most cities, you could drive across a neutron star in about 15 minutes if there were a road, which of course there couldn't be, because the gravity would destroy you long before you arrived. An object smaller than a city that may contain forms of matter found nowhere else in the observable universe. A place where quantum mechanics, general relativity, and nuclear physics collide at their most extreme. A natural laboratory that we can observe but never visit, never recreate, and perhaps never fully understand. All balanced on the knife's edge between quantum pressure and gravitational collapse. An object that has been spinning since the moment it was born in one of the most violent explosions in the cosmos, and will continue spinning for billions of years, slowly cooling, slowly fading, but never losing its fundamental nature. Because the quantum stubbornness of neutrons, their absolute refusal to share the same quantum state, will hold the star up essentially forever. Unless something adds enough mass to push it over the Tolman-Oppenheimer-Volkoff limit. Then, in an instant, gravity finally wins the war it's been fighting since the moment the star was born, and the neutron star vanishes, replaced by a black hole. The Pauli exclusion principle held gravity at bay for billions of years. But gravity is patient, And gravity never forgets. We live in a universe where the same quantum mechanical principles that give structure to the atoms in your body, the same Pauli exclusion principle that determines the arrangement of electrons in your cells, also hold up objects containing more mass than the Sun against gravitational forces that would crush anything else into oblivion. The physics that makes you possible is the same physics that makes neutron stars possible. You and a neutron star are governed by the same fundamental laws. The difference is just a matter of scale. In a neutron star, those laws are pushed to their absolute extremes, tested in conditions we can't replicate, operating at intensities we can barely calculate. And they hold. The laws of physics hold, even in these most extreme environments. That's either comforting or terrifying, depending on your perspective, but it's certainly beautiful. Neutron stars are among the most extreme objects in the observable universe. They compress more physics into a smaller volume than anything else we know of except black holes, which don't let us see what's inside. Neutron stars are extreme, but they're not hidden. They pulse, they glow, they vibrate, they merge, and every signal they send us carries information about the conditions inside them. They are, in the most literal sense, messages from the frontier of physics, written in X-rays and radio waves and gravitational waves, and we're only just learning to read them. Every new telescope, every new gravitational wave detector, every new theoretical breakthrough brings us closer to understanding what lies at the heart of these extraordinary objects. We may solve the hyperon puzzle, we may confirm the existence of quark matter in neutron star cores. We may discover that the inner core contains something we haven't even imagined yet. The answers are out there, encoded in the light and gravitational waves streaming toward us from neutron stars scattered across the galaxy. We just need to keep looking, keep building better instruments, keep asking better questions, and keep pushing our understanding of nature to its limits and beyond. Because that's what neutron stars do. They push the limits of nature itself, and in studying them, we push the limits of what it means to understand the universe we live in. Thank you for taking this journey with me tonight. From the explosive death of a massive star to the quantum heart of the densest objects in the cosmos, we've explored something truly extraordinary. Next time you look up at the night sky, remember that scattered among those points of light are neutron stars, objects smaller than a city, denser than an atomic nucleus, spinning hundreds of times per second. Each one a laboratory for the most extreme physics in the universe. Each one a message from the frontier waiting to be decoded. Good night. And may you never think about a teaspoon of matter the same way again.